Okay, so this is a video to help you work through chapter 2 of the applied year 2 work whilst you're at home. It's all about probability, specifically conditional probability, which we'll talk through what that means and how that affects how you would answer questions compared to what you've done in the first year. So I'm just going to go through some of the basics and help you with a couple of examples to get you started on the first exercise. So hopefully you remember from the first year on probability that we can represent probabilities in Venn diagrams, specifically using set notation. So I've got some examples here of how we would write what the yellow sections represent in set notation. So the first one, I'll just give you a second to think about what that might mean. And hopefully you've worked out that that means it's the intersection of A and B. So that's A at this, so it shows A and B, the area that's in set A and in set B. So it's A and B, and in set notation we use the intersect, the N symbol. For part 2, I'll give you a second to look at that. And this time we've got all of A coloured in and all of B coloured in and the middle section as well. So that shows anything in set A or in set B. And we use the union symbol for that one. So that's A union B, A or B. And then for the third one, again, I'll give you a second to look at that. That one's fairly easy to work out as well. If you look at what's white rather than what's yellow, and the bit that's white is A, so anything that's yellow is not A, and to show not in set notation, we put a little dash after the set that we're not having, so that would be A dash. Okay, so that's a bit of a recap on set notation, the 3 symbols that you need to be able to use. We can represent any probability using those 3 symbols, the intersect, the or, and the not. Any combination of those 3 symbols will be the 3 symbols that we use in set notation in any probability to do with Venn diagrams and other situations as well. So we will have talked about independent events in year 1, and just as a bit of a recap, I just want you to think about what it means if events are independent and anything else you can think of to do with independent events. We talked about independent events to do with Venn diagrams. We had an equation to do with independent events, and I'd just like you to think about that for a second. Okay, so independent events are events where the outcome of one event doesn't affect the other events and their probabilities. So if I flip a coin twice, the outcome of the first event, the outcome of the first flipping of the coin, whether that's a head or a tail, has absolutely no impact on the second flip of the coin. If I get a head on the first flip, it doesn't mean I'm going to get a head or a tail on the second flip. It's not going to affect those probabilities. It's still going to be a 50% chance of getting a head on the second and a 50% chance of getting a tail on the second. They've had no effect. So that's independent events. And I mentioned that there was a formula to go with that, and there is, and that's that if events are independent, so this only works when events are independent, the probability of both events occurring, so the probability of A and B occurring, or A intersect B, we can now write, is equal to the probability of the first event occurring times by the probability of the second event occurring. And this is a formula that's really useful when we have independent events. I mentioned Venn diagrams. This can be used as a test for independence when we're working with Venn diagrams. If I just give you a quick example of that. If I've got two events A and B, and let's say the probability of the intersect is 0.3, if I've got 0.7 and 0.2 here, that's not going to work because that adds up to more than 1. Hang on a second, I need to think about this a bit more carefully. Let's put 0.5 here, 0.2 here, and 0.1 on the outside. Okay, so we can test if events A and B are independent in this example by checking if the probability of A times the probability of B is actually equal to the intersect. So probability of event A is 0.7. Probability of event B is 0.4. And if that happens to come out as 0.2, then the events would be independent. Now that does not happen here. This comes out as 0.28. And therefore we would be able to say that the events are not independent. On the EdXL course, that's quite a common exam question to test for independence. Okay, so I'm just going to go through an example or two of how the questions work in exercise 2A that will help you work through the exercise questions, hopefully. A card is selected at random from a pack of 52. You might be asked to fill this out in a textbook question. You wouldn't be asked about playing cards in an exam. They can't assume that you know how many cards there are in a pack or how many aces or anything like that. But they do tend to use playing card examples in the textbook, but not in the exam. So A is the event that a card is an ace, and D is the event that the card is a diamond, and we want the probability that the card is an ace and a diamond. In other words, the ace of diamonds. And we can see in the intersect that there is one card that is an ace and a diamond. And it says in the question that there are 52. You may or may not have known that anyway. So that's quite straightforward. For part B, it's A or D. Now in this case, the events are not independent. Choosing an ace will impact on the next card being a diamond and so on. So we can't just add the probability of it being an ace and the probability of it being a diamond because they are not mutually exclusive. So what we're going to do is we're going to look at these three numbers and add these three numbers together. So that's going to be 16 out of 52. In your exam, they're really not going to care if you cancel your fractions down or not. I will do. So that one cancels to 4/13. Just a bit of a check that you understand the notation again. This wants the probability that the card is not an ace. Again, if you think about playing cards, you know how many cards, hopefully you know how many cards there are that are aces, and therefore how many cards aren't aces. But if we want the cards that aren't an ace, I'm going to want the diamonds that's not the ace of diamonds, so just the 12 and the 36 that are not aces or diamonds. So that's going to be 48 out of 52. And again, we can cancel that down as well. That will cancel to 12/13. And then if you just have a quick look at the last one before I work through it, it wants the probability of not A or D. Sorry, that's not A and D, the intersect. Probability of it being not A and the probability of it being D. So that's a little bit trickier to work out. I'm just going to go through a method I like to use sometimes if you do have a trickier question like this. And that's to shade. If we think about the first slide that I used, we shaded some sections to help us identify the set notation. We can do it the other way around as well. Not A would be anything that doesn't include the circle on the left. So that's what I've shaded there. I've shaded not A. If I now shade D as well, so we shade what they want in the question. And then we need to think about the section that we actually want. So we want the intersect. Now, for the intersect, that's going to be the bits of the Venn diagram that have both of the shadings, the red shading and the green shading. And that's this section here. And we can then take the probability. So that's 12 out of the 52. And that would cancel down to 3/4. No, it wouldn't. 3/13, sorry. I've got a second example without the Venn diagram, and it says that probability of A is 0.3, probability of B is 0.4, the intersect of A and B is 0.25. Explain why A and B are not independent. So we can use that formula that I mentioned earlier, and that is that if events are independent, then if you times the probability of each event together, then it will equal the intersect. But if we do that here, we don't get 0.25. So the formula doesn't work. So since it says explain, so we need some words. Since 0.12 is not equal to 0.25, the events are not independent because the formula doesn't work. It then says, given also that probability of C is equal to 0.2 and A and C are mutually exclusive and B and C are independent, draw a Venn diagram. Okay, so we've got to take all of that information and put it into a Venn diagram. Now there are 3 events. So you can draw these 3 events as 3 overlapping circles, but we don't actually need to. We can draw them in a straight line because they've told us that A and C are mutually exclusive. And mutually exclusive, hopefully you remember, means that there's no intersect. If we're talking Venn diagrams, it means there's no intersect. So I can draw A, B and C like this because A and C don't need to have an overlap. Okay, so we already know a few things here. We know that A intersect B is 0.25. We know that probability of A in total is 0.3. So all of this circle together needs to be 0.3, which means this needs to be 0.05. We can do the same thing for B. B is 0.4. We've already got 0.25. So we can't fill that in yet because all of this needs to be 0.15. We know that the next thing we're going to use is the fact that B and C are independent. That means we can use that formula. So probability of B times the probability of C needs to equal the intersect. B was 0.4, C was 0.2. which means the overlap is 0.08. So that can go in here. And then we can take this 0.08 away from the 0.15 to get the part that's B but without the A and the C. That's going to be 0.07. So get rid of this now and put 0.07 in there. We can then use the fact that the probability of C needs to equal 0.2, which means this is going to be 0.12. And then the last thing we need to do is add all of these numbers up to see what else needs to be on the outside. So 0.3 for A plus 0.15 plus 0.12 gives me, what's that, 0.57. So on the outside here we're going to have 0.43. Okay, and then the final part of this example says find this probability, which looks quite scary. It's the probability of A intersect not B. So the probability of A and not B. Or we can add on the probability of C. So let's work out what the probability of A and not B is. So we can do that again using the highlighting technique. The probability of A and not B I'm doing that wrong. Not B. It's the intersect, so we want the section where we have both highlighted sections, and that is this section here. So that's the 0.05. Or the probability of C. Now with this, we are allowed this section of B here because that is separate to the first requirement. This requirement just says or C. It doesn't care whether B is involved or not. So I am allowed the 0.08. So we're going to add on the whole 0.2 and get an answer of 0.25. That's quite a common error that people make, is that because B was discounted in the first criteria that we think we need to discount it in the second as well. That is not true. These two are completely separate things. I've worked out the probability of A intersect not B. That's the 0.05. And now I'm just going to add on, because it's a plus, it's an or, the probability of C. Probability of C was 0.2. That's the end of the story, okay? So don't worry that I discounted B in the first part and then I've included it in the second. That is the correct thing to do. Okay, hopefully those examples will help you work through exercise 2A. It starts on page 19 of the Edexcel Year 2 book. If you've got any problems, any questions, just leave a comment or ask on Show My Homework, and hopefully your teacher will get back to you. I'm happy to answer questions even if I'm not your teacher.